I'm Sculptor. I'm from mechanical engineering. So my topic is insight into the cell in a mechanical and physical perspective. I will start the introduction with some brief introduction on the multi-scale in human body. So if we see from this is the length scale arrow here. If so, we see from this part, the right part, so we can see the human body. And if we look into our head, we can see the brain, right? Both these two parts is really large because we can clearly see from our own eyes. So we call it micro scale here. And if we want to look inside, so we can use optical microscope, and we can see the neuron cells here, right? And a lot of neurite here. So in this way, the order is really smaller. It's called meso scale here. And we can go on to step into the micro scale here, and we see the actin filament. In this way, we can have already used the electron microscope here. Interesting thing is we can still go on. We can step into the nanoscale here. In this way, if we want to know something in the molecular basis or the molecular level here, there may be a problem here, because if we use the electrical microscope, we did a prefixing of these cells, which means we could only observe the static state of the cells, because in this way the cell already died, right? So we could only observe static part. But in reality, if we want to see these proteins, we need to know how it works, right? We need to know the mechanism behind this kind of protein. So I can show you a video here. Yes. So this is one of the proteins they called myosin here. If you see here, you see how it works. In fact, just like us, we can walk in this way. It's called random walk of it's also called the motor protein, and we will show later why this would happen. Although this is animation here, but it's quite scientific and accurate in physics, in fact. And so this is the main question here. If we want to know how this works, we need to use another perspective, the perspective from mechanical and the physical part. So I will start my introduction on the migration of cells. So the migration of cells is very important, and it's also a very simple process. So this picture clearly shows the process of the migration of cells. So this is first step here. The first step for a cell to migrate is to get a protrusion part this way. And if we look inside here, we could see a lot of fingers-like protrusion part here, and we call it filopodial. And the main component of this filopodia is actin filament, like this way, a lot of filament here. And if we look inside, the actin monomers is the main component of this actin filament here. So this is just like the brakes for this whole structure here. Okay, so we go back to the migration part. So this is the first step, the protrusion part, and then we go to the second step. The adhesion will form at the tip of filopodia. Here, the green dots here. This is the adhesion molecules, and so the third step is this kind of molecules could attach to the substrate and give a force to drag the whole cell forward here. And finally, the adhesion molecules would break or disassemble at the end part here. So in this way, the cells would move forward. So this is the whole process of the cell migration here. So until now, what I have taught is quite biological thing, right? So I haven't introduced the mechanical part. So in fact, for mechanists and the physicists, what we are interested is on the force. So there are two main questions here. The first question is, what force causes the filopodial to protrude? Because we first get a protrusion part, right? So what kind of force that gives it a protrusion? This is the first question. And the second question is, where the drag force comes from? Because I have said in the third step here, the whole cell body was dragged forward. So there must be a force here to exert this force. So this is two main questions here. So we will solve this question one by one. Okay, the first question can be solved by the Brownian Ratchet model. It's very simple. We can divide this Brownian Ratchet model into two parts. The first part is called the Brownian motion. I think you have already learned in your high school, if you put a relatively large particle in the liquid or in the water, this kind of particle could move irregularly, right? The reason is very simple, because it will collide with a lot of other smaller particles here, molecules, right? So it could move in this way. We also call it random walk. Another part is ratchet. So what's ratchet? If you go to the MTR station, every time you go through this gate, if you think about this one, the main mechanism behind this kind of thing is that it's just as this gear here. So that's why it could only give you in one direction entrance. You can't go back. So this is the ratchet. So these two parts combined, so we call it Brownian Ratchet model. Okay, I will show you how this Brownian Ratchet model can explain the filopodial protrusion. So this is the actin filament I have shown you before, and this D represents the membrane here. And the membrane could go through a Brownian motion, so it could move irregularly here. And so there will be a gap between the actin filament and the membrane here. So once the gap is large enough, the actin monomers could assemble at the tip, which is also the polymerization here. So once it assembles here, the membrane won't go back, right? Because they give it a force here. So this is called ratchet here, and this is Brownian motion. So these two parts is constituted into the Brownian Ratchet model. And in reality, things may be much complicated because a lot of other proteins may participate into this process. We look at this figure here. But this model is very simple and effective in explaining a lot of interesting phenomena in physics and biological science. So one is the application of this model here is the bead propelling. If you look at this figure here, this is the bead. If we put the bead in the micrometer size with some proteins, actin filament, so according to the Brownian Ratchet model, there will be force given on the bead, right, on the contact edge here. So in this way, the bead could move in a certain trajectory, like this way. So this is, in fact, this is the experiment done by one of the senior students in our lab. It's a very simple and interesting experiment. Okay, so we go on to the next question is about where the drag force comes from. That we have mentioned about this drag, the whole cell body forward. So if we look at the adhesion here, we amplify again. We see this kind of, it's called focal adhesion part. And the focal adhesion part, below this focal adhesion part, there will be a lot of integrins, which is also called adhesion molecules. There will be a lot of other kind of proteins. We will attach with the substrate, this kind of structure here. And after the focal adhesion here, there will be a lot of stress fibers. Stress fibers are like this way. And in fact, a very important protein is called myosin, or the motor protein would exist here. This one, in fact, would generate a force that drags the whole cell forward. So how to interpret this one in a mechanical way? So we can think this one. This is a mechanical device, in fact. This is myosin motors, just like this one, and the stress fibers here. At the linear edge of this stress fiber, there's a lot of the springs. The springs is just the integrals, and we call it molecular clutches. So why it's called clutches? If you think about this one, it's very interesting. It's quite similar with the brake pedal in the car, right? So the main component of the brake pedal is the clutches, and this is also clutches, which means when there is a force, large force, the molecular clutch will be brake. And if there's no force or smaller force, the clutch will stay here. So this is how it works. So it's quite mechanical way to think about this question. Okay, I have introduced these two models. So I will go on with my project. So my project is on filopodial protrusion part using these kind of two models and other simple models here. One of our collaborators manufacture a lot of interesting substrate. Here we use some different size diamond coating. If we use very small diamond coating here, the surface is very smooth. The large size coating is very rough here. And we put the cell inside on the surface and let it grow, so we can see a lot of filopodia grow on this kind of thing. Interesting thing is we can use fluorine labeling to label this filopodia, and so we can track the trajectory of this filopodia. And so we can plot the length or distance with respect to time curve like this way. So first thing we can do is we use some filopodia bending model, because in this way we think the filopodia as a beam. So once it's a beam, it will bend due to the adhesion force here, or some its own weight, so it will bend like this way. And so this way we can restore how the shape look like in the real substrate. We look like this way. So this is a simulation result. Topography and the filopodia is the red line here. If we can go on, we can combine the models we have introduced before, the Brownian Ratchet model and the molecular clutches model. In this way, we can use the simulation. This blue line is our simulation result, and the red dot is the experiment data, in fact. So we can see the clear, very good match here. So we verify our model, and also we can predict and explain why the velocity was different at different substrate. At a very small substrate here, the velocity will be relatively large in this, and at very rough surface, the velocity will be decreased a lot in this value here. So it's explanation here, and yeah. So the final part is I got summary here. So I have already introduced these three models, and also I restored the shape, explain the movement of filopodia protrusion on rough surface. This is my project. And the reason why the new perspective is very important, because it can help us to explore the intrinsic and dynamic mechanism behind this cell activity. And secondly, we can quantitatively measure and predict the thinking process of cells. Thirdly, it can inspire us to manufacture some device according to this kind of models. And finally, there's also an interesting video here. Yeah. Okay, this is adhesion part, and they will form a focal adhesion here, focal adhesion form. And then this is motor clutches, if you see this one. So it attached with this, form a spring part. And this one is myosin, the motor thing, and we will transport some kind of things here. So this is animation, and I searched it from the YouTube. It's called The Inner Life of a Cell. It's a long video. You can search it in the YouTube. And finally, I want to say, using this kind of modern thing to explain and predict the biology thing, it's quite interesting and beautiful. That's why it was our effort towards this topic. Thanks.
when you said cell migrate,
Yeah.
you mean cell inside your body move from one part to another?
Yeah, right. Because if we think, because all cells are produced from one single cell, right? The cell will produce and finally will work. That may be a long distance. So the cell needs to migrate from this part to the other part. So that's why it's a very important process here, migration of cells.
Does all cells migrate?
In fact, I'm not sure. In fact, it should be no.
So what cells will migrate more than
Yeah, cancer cell will be more. In fact, I think a lot of cells, besides the blood cells, all this kind of thing, in fact, they will move in another type of cells.
So the cancer cells are not spread through the blood. They actually